Welcome to the deep dive. Today we're jumping into something really critical, high stakes for sure. Getting weather forecasts right, not just days out, but hour by hour.
Yeah, it's essential. We've made huge strides with deep learning for those medium-range forecasts, maybe 10, 15 days out. Pretty amazing stuff.
Totally. But look closely, and those forecasts, they usually only give you a picture every 6 hours.
And 6 hours.
Yeah.
Well, it's basically an eternity if you're managing an energy grid or running complex transport or even just trying to prep for rapidly changing severe weather.
Right. So that hourly prediction, it's remained this critical challenge, as our sources put it. Trying to get current AI models to predict hour by hour just doesn't seem to work well over time. They tend to break down.
They become unstable, yeah. The errors just pile up.
So that's our mission for this deep dive. We're looking at sources introducing a new framework called FlowCast-ODE, designed specifically for this hourly problem.
And they really zeroed in on two big roadblocks. First, that error accumulation problem you just mentioned, how forecasts get wildly inaccurate when you try to chain hourly predictions together.
Okay, the instability.
Exactly. And second, something maybe even more fundamental. The training data itself, the main data set everyone uses, ERA5, actually has these built-in jumps, temporal discontinuities.
Non-physical flaws in the data they train on. Wow.
Yeah, it's a tricky one.
So if the usual way fails because of errors and faulty data, how does FlowCast-ODE tackle this? What's the core idea?
Well, instead of thinking about time as these separate snapshots, FlowCast-ODE treats the atmosphere's changes as a continuous flow, like a smooth video, not stop-motion frames.
Okay. Using some sophisticated math like ordinary differential equations to keep things stable and smooth over time.
Precisely. It models the dynamics continuously.
Let's dig into why the simpler approach fails first. Why can't you just, tweak existing models for hourly outputs? It sounds easy enough.
It sounds easy, but the way these models work, this autoregressive rollout, it's like a game of telephone.
Ah, okay.
You predict hour 1 based on the real weather, fine. Then you predict hour 2 based on your hour 1 prediction, which has tiny errors. Then hour 3 is based on the slightly more error-filled hour 2 prediction.
And those tiny errors just multiply like crazy.
Exactly.
Yeah.
Exponentially. So by the time you get 120 hours out of 5 days, your forecast might be completely off the rails, just noise.
Right. And you mentioned this is made even worse by the data they learn from, the ERA5 dataset.
Yeah, that's the paradox.
Yep.
ERA5 is fantastic. It's the gold standard reanalysis data. But it has this quirk because of how it's made.
How so?
It combines model forecasts with actual observations in what's called an assimilation cycle. And it does this every 12 hours.
Okay, so it's sort of correcting itself with real-world data periodically.
Right, but the process of stitching that observation data into the ongoing model forecast creates these, discontinuities.
Yeah.
Seems, like you said earlier, where the model state jumps in a way that isn't strictly physical. Exactly. The sources are quite specific. They point to these physically unrealistic jumps happening around 09.00 to 10.000 UTC, and again, around 21.000000 UTC.
Okay, specific times linked to that 12-hour cycle.
Yeah. So if you try to train a model to learn smooth, continuous atmospheric physics, but the data itself has these artificial leaps every 12 hours.
The model learns the leaps, it learns the wrong dynamics.
Precisely. Which just makes that instability problem even worse. It accelerates the error growth.
You're basically teaching it physics with a textbook that has weird jumps in it.
That's a good analogy. And this whole issue is likely why the previous best approach, Pangu-Weather, needed such a complicated setup, isn't it?
Right, Pangu-Weather, they didn't use just one model.
No, they built this whole hierarchy. 4 separate models, actually. One for 1-hour steps, one for 3-hour, one for 6-hour, and a big one for 24-hour jumps.
Wow, 4 models just to get a stable forecast.
It helped with stability, yes, but it created its own problems, like predicting 72 hours ahead meant using the 24-hour model 3 times. Simple enough. But predicting 71 hours, that involves some awkward combination of the 24-hour, maybe the 6-hour, the 3-hour, the 1-hour models. It gets messy.
So the path the prediction takes changes depending on the exact forecast length. That sounds inconsistent.
It is. It lacks what they call temporal coherence. And it's computationally heavy, managing all those different models.
Okay, so that sets the stage for FlowCast-ODE. If the old way is like stop motion with compounding errors and data glitches, what does this continuous flow actually look like?
Think of it less like predicting discrete future snapshots and more like understanding the flow itself.
Mm-hmm.
The model learns the velocity field, basically, the direction and speed of change for all the atmospheric variables at every point.
Ah, so it's learning the process of change continuously.
Exactly. It uses the mathematics of ordinary differential equations, ODEs, to describe this continuous evolution. This naturally aligns better with how physical systems actually work.
More like capturing the physics directly.
Yes. And this continuous view is inherently more stable than chaining discrete, slightly wrong predictions together.
Okay, that sounds elegant. But how does this elegance deal with the messy reality of those ERA5 data jumps? They didn't fix the data, right?
No, they couldn't fix ERA5. Instead, they developed this clever two-stage training process specifically to mitigate the impact of those jumps.
Right, stage one.
Stage one is about learning the core physics, trying to ignore the data noise as much as possible. They train their flow model, but only using data at 6-hour intervals.
Okay, coarser steps.
But crucially, they only use the data points from 00.0006.0, 12.000, 12.000 UTC.
Uh-huh. They specifically avoid the times around 9.0000000 UTC where those non-physical jumps happen.
Exactly. By training on these cleaner 6-hour snapshots, the model gets a much better sense of the true underlying atmospheric dynamics without being confused by the assimilation artifacts.
That's smart. Isolate the good data to learn the fundamental flow.
That's the core mitigation. Build the foundation on the most reliable parts of the dataset.
So once it's learned those core 6-hour dynamics, how does it get back to generating the hourly forecasts needed? That's stage two.
Right, stage two is the refinement. It takes the smooth, continuous dynamics learned in stage one.
The flow field, essentially.
Yes, that learned flow field. And it uses an ODE solver, like a mathematical integrator, that uses the explicit Euler method to essentially play that flow forward in time, generating the states at every single hour mark.
So it's not making independent hourly predictions one after another.
No, that's the key difference. The ODE solver ensures that each 1-hour step is just a point along that smooth, continuous trajectory defined by the dynamics learned in stage one.
Ah, so the hourly steps are derived from the continuous flow, guaranteeing they're consistent and stable over time.
Exactly. It provides that temporal coherence Pangu-Weather's multi-model system lacked.
And this is all done with one model, not four.
One single FlowCast-ODE model handles the whole process. It learns the 6-hour dynamics, and then the ODE solver generates the hourly outputs from that single learned flow.
That's a huge simplification operationally. Less complexity, more consistency.
A massive win, yeah. Deployment, updates, everything becomes simpler. And your 5-day forecast is generated using the exact same underlying physics model as your 1-day forecast.
Okay, let's get into the results. The proof, as they say. How did FlowCast-ODE stack up against others, like Pangu-Weather, on standard global accuracy metrics, like RMSE?
Pretty impressive, actually.
Oh.
Looking at 5-day forecasts, so 120 hours out, FlowCast-ODE generally had lower root mean square error for key things like sea level pressure and the 500 HPA geopotential height.
Lower error is better, obviously.
Right, and this held true across pretty much all the lead times they checked.
Now, didn't you say FlowCast-ODE has to take way more steps, like 120 hourly steps compared to Pangu-Weather's 5 24-hour steps for the same 5-day period?
I did. That's what makes the low errors so remarkable.
Uh-huh.
Even though it's iterating 120 times, the continuous flow approach and the ODE solver are so stable that the error doesn't accumulate badly.
It resists that snowball effect we talked about earlier.
Exactly. It's strong evidence that the core concept works. Modeling continuous dynamics prevents the error explosion you get with discrete steps.
Okay, so global error scores are good, but what about the quality of the forecast map? You don't want something that's just statistically accurate but looks blurry or smoothed out.
Right, you need the details. That's where they looked at power spectra.
Explain that a bit. What does it show?
Power spectra analysis basically measures how much energy or detail the forecast map retains at different spatial scales, from large weather patterns down to smaller features.
Okay, more energy means sharper details.
Generally, yes. If a model loses too much spectral energy, especially at smaller scales, the forecast looks overly smooth or blurred out, like a low-resolution image.
And FlowCast-ODE.
It consistently kept higher spectral energy compared to Pangu-Weather, meaning it did a better job preserving those fine-scale details, sharper fronts, tighter pressure gradients, less artificial blurring.
That sounds crucial for predicting things like intense local weather.
Absolutely. And that leads into how it handled extreme events, specifically tropical cyclones.
How did they test that?
They tracked 6 major typhoons from 2021. Now, here's the interesting part. FlowCast-ODE was running at a 1-degree resolution for this test.
Okay, that's fairly coarse for tracking typhoons.
Right. Pangu-Weather, the baseline they compared against for this specific task, was using its high-resolution 0.25-degree model, a big advantage in terms of detail.
4 times the resolution, basically. You'd expect Pangu to do much better.
You would. And initially, for the first day or two, Pangu did have a lower track error. But
Yeah.
beyond about 48 hours, FlowCast-ODE's track error, its mean absolute error, became pretty much statistically indistinguishable from the much higher resolution Pangu model.
Wow. So the better time dynamics, the flow coherence, somehow compensated for the lower spatial resolution in the longer run.
It really seems that way. It suggests the stability and physical realism of the FlowCast-ODE approach provides significant benefits even when resolution is lower, especially for longer-term tracking.
That's a powerful result. Any other validation metrics?
Yeah, one more key one. Energy conservation. Real atmosphere physics conserves energy, more or less. Good models should reflect that smoothly over time.
Okay, so how did the energy components like kinetic and internal energy look in the forecasts?
FlowCast-ODE showed a noticeably smoother energy trajectory over the 5-day forecast. It followed the overall trend in the ERA5 reference data very closely.
And Pangu.
Pangu-Weather's energy trace showed more fluctuations, likely because it's switching between those 4 different models with different step lengths. It wasn't quite as smooth or continuous.
So the continuous flow model produced more physically realistic energy behavior over time. Another win for that core idea.
Yeah, it adds confidence that the model isn't just getting the right numbers, but it's reflecting the underlying physics more faithfully.
Let's talk efficiency again. The ODE approach is stable, accurate, but sometimes solving ODEs can be computationally demanding. How did they keep the model relatively lightweight?
Good question. Part of the magic is in the model's internal architecture. They use something called a low-rank ADL-N0 temporal modulation mechanism. Bit of a mouthful.
Okay, break that down. What does that do?
Essentially, it's a very efficient way for the model to understand when in the forecast it is. It adjusts the model's behavior based on the time step.
And the low rank part is key for efficiency.
Exactly. Low rank in this context means it uses a compressed, simplified representation for that time information. It doesn't need a huge number of parameters just to handle the time aspect.
So it saves parameters, making the model smaller.
Yes. It lets the model dedicate more of its parameters and computation to the really hard part, predicting the complex spatial patterns of the weather while keeping the time handling part lean.
What was the actual impact on model size?
They managed to reduce the total number of parameters by about 15% compared to what you might expect, down from around 54 million to about 46 million.
15% smaller with no loss in accuracy. That's significant.
Definitely. Lighter model, easier to train, potentially faster to run, even with all those ODE steps.
So thinking about this single model versus Pangu's 4, you get the hourly output, the stability, the accuracy. Are there any potential downsides to consolidating everything into one ODE framework? Maybe it's not quite as tuned for specific short-term steps.
That's a fair point to consider.
Right.
While it does require more sequential steps, the sources argue that consistency outweighs that. You avoid the whole complex pipeline management of running 4 models and stitching results.
Right. The simplicity and coherence is the main game.
Exactly. The overall package seems to be the big win. High accuracy hourly forecasts, good temporal coherence, it's efficient with fewer parameters in one model, and it's specifically designed to handle those known issues that the ERA5 data.
It really feels like a well-thought-out solution addressing multiple problems at once.
It's definitely a significant step forward, tackling both the instability of autoregressive forecasting and cleverly working around the data discontinuities using that continuous flow idea.
So, wrapping up the achievements. We've got stable hourly forecasts, much less error building up over time, better preservation of fine details in the forecast maps, and it holds its own even in tricky situations like tracking typhoons, all while being more efficient.
That sums it up well.
Are there limitations? Things it doesn't do yet?
Yeah, the authors are upfront about a couple of things. First, the current 1-degree resolution, while decent, probably limits its ability to capture really small-scale extreme weather phenomena accurately. You'd need higher resolution for that.
Okay, resolution is one area for future work.
Right. And second, for real-world operational forecasting, you almost always need ensemble forecasts. That means running the model many times with slight variations to gauge the uncertainty. FlowCast-ODE, in its current form, doesn't have native support for generating those ensembles easily.
So uncertainty quantification is another next step. Makes sense.
Yeah, both are key areas for future development to make it fully operational.
Okay. This has been a really fascinating look at how rethinking the concept of time in these models, moving to continuous flow, can solve some really stubborn problems. We want to leave you, our listener, with a final thought to mull over.
FlowCast-ODE is impressive because it engineers a way around those artificial 12-hourly jumps in the ERA5 data.
Okay.
It mitigates their impact.
Right, it doesn't fix the data. It works despite the flawed data.
Exactly, and that raises a much bigger question for the whole field, doesn't it?
Which is?
If ERA5, the data set basically everyone relies on for training these powerful AI weather models, has these built-in, physically unrealistic glitches every 12 hours,
Right.
how many other weather AI models out there are also being subtly tripped up or limited by this?
Are we optimizing models to perform well on imperfect data rather than pushing for fundamentally better, more physically consistent foundational data in the first place?
It suggests there might be this underlying data integrity issue affecting progress across the board that needs attention, a deeper problem for the whole community to potentially address.
A really profound point about the foundations we build on, something to definitely think about. Thank you for diving deep with us today.